So, what is quantum tunneling? Well, it's the idea that a particle can pass through a barrier without ever being found within the barrier. Imagine a mass on course for an obstacle. The mass is going to want to continue on the path that it's on, but sometimes the mass isn't capable of overcoming the barrier, and that's when quantum tunneling comes in. The success of quantum tunneling is basically dependent on two major things: a slim barrier and a small mass. Because the mass has to be so minute, though, quantum tunneling is only likely for things of the quantum realm, such as electrons, which are particles. So we can't walk through walls, and trust me, I learned that the hard way, but then how can an electron go through a barrier? The key is that the electron doesn't physically move through the barrier in the way that you would expect, and that's what makes this phenomenon remarkable. For instance, imagine a paper being held to a fridge by a magnet. The electrons naturally want to flow from the magnet into the metallic fridge, so the electrons can tunnel through the non-metallic barrier, but they won't be found within the paper. And when the thickness of the barrier increases, the probability that the particles will be able to tunnel through the barrier decreases. So if there isn't an increase in the number of electrons to compensate, the small magnet's job of holding up the papers becomes nearly impossible. I think of the effects of quantum tunneling in the way that sound travels, because sound echoes off walls and sometimes can be heard through walls, in the same way that electrons can bounce off barriers and sometimes can go through barriers. The sound vibrations and energy volumes won't be nearly as great in magnitude in comparison to the side that they started on, but there's still going to be some, and that's what allows us to observe them. Thank you, that's all.